Lesson 1-6, Transformations of Functions. It's MA 912 F 2.2, 2.3, and 2.5. So some key things about 1.6 in transformations. We have parent functions. Parent functions are our base graphs that we have. We have our constant graph, which means it's a fixed number. So basically you're plotting an equation on the y-axis, and that's all it is. Then we have our identity graph, which is f of x equal to x, where we are seeing our first line situation, which means this is also where we see our y equals mx plus b. Then we have our absolute value functions. We just finished learning about those, where we have f of x equals the absolute value bars of x. Again, notice that domain is always all reals, and our range is also depending on where the lowest y value is. So in this one, the y value is at 0, so it's going from 0 to infinity. The next one we have is our quadratic functions. It's our U-shaped graphs. One thing about them is the domain and our range are similar and interchangeable with our absolutes. They are basically the same, just depending on where they are. A translation for us is a transformation in which a figure is slid from one position to another. You're sliding left and right without being turned. So it means I am shifting. So we have one where we can say we're shifting it on the y-axis. So it's where we have a plus k. And if the k value happens to be bigger than 0, then it's opening up. If we are less than 0, it's opening down. Now when it's changing on the inside, the changes on the inside of the equation, it's where we become sliding left and right. So for example, the first one is like y equals, say, x squared plus 2, means I shifted my parabola, in this instance, up 2 units. If I had y equals x squared minus 2, I'm shifting it down 2 units. If I see y equals parentheses x plus 2 squared, because now the numbers on the inside is being shifted to the left 2 units. And then if I did y equals x minus 2 squared, it's always the opposite of what we see. We're shifting it to the right 2 units. In example 1, we're doing a translation. So they wanted us to graph g of x, the transformation of f of x equaling x squared, translated down 4 units and left to the 2 units. So they want us to translate it down 4 units and then left 4 units. So because f of x is equal to x squared, our original, they want us to change our values. So since we're translating it down 4 and left 2, HK happens to be the changes. So this is our X and this is our Y change. So our H in this instance is we're translating it left 2 units. So we wanted to shift 2 units to the left, and we want to go down 4 units. That's why it's going to be -4 for the K value. So when we take our original equation, we went from a y equals x squared, and they want us to do x minus h squared plus a k value. That's what we're changing for. So we're substituting in for h and k. So now that's why you see x minus, and then that's a -2 squared plus a -4. And that's where we came up with our new equation, which is y equals x plus 2 squared minus 4. You can make a table of values and then substitute in, and it would show you the change. Or basically, since we know what our graph is starting, here's our original. We went to the left 2 units. This one moved to the left 2 units, and then down 4 units. Left 2, down 4. And you pick 3 points, and you're going to apply the same situation to all of them. When we look at example 2, example 2 is talking about identify translated functions from graphs. So it says the graph of the absolute value function with a parent function. Again, absolute values, referring back to our notes, we know is y equals absolute value of x. Notice that the vertex of the function has been shifted both vertically and horizontally from the parent function. So we need to figure out what our shift is. Our original h is here at 0, 0, and we shifted 1 to the right. So we shifted 1 to the right. There's my h. And then from our parent position, we started at 0, 0, and we went up 2 units. So we went up 2 units. So when we write our g of x equation, it's now g of x equals absolute of x minus 1, because we need to do the opposite of what we had, plus 2. Again, opposite sign in absolutes or parentheses. You will leave the opposite sign in absolutes or parentheses. So if you're shifting to the right, you need to be a minus inside. If you are shifting to the left, you are a plus inside. Dilations are a transformation that stretches or compresses the graph. So it's going to stretch or compress the graph. Multiplying usually by a constant will dilate the graph with respect to the y-axis. If you're multiplying by an independent variable, which means it's a fraction, it's going to dilate in respect to the x-axis. So, again, some key concepts. If the value of your graph of the a value, what being multiplied, is greater than 1, it's vertically stretched, which means it's approaching the y-axis. If it's in between 0 and 1, when we're looking at it, it means it's bringing it down closer to the x-axis. Then obviously, if you have a flip of it on the inside, it's where it's going to be stretched more horizontal compression, and then a vertical compression. A reflection, remember, that's where you're doing the figure, line, or curve, and it's being flipped on the line of reflection. So normally it's over the x or y axis when we're flipping them. So normally if it's being done in f of negative x, it's an x-axis reflection. If it's on the inside, then that's where we have a reflection over the y-axis. In example 3, it says horizontal dilations, graph g of x, the transformation of f of x equal to x squared compressed horizontally by a factor of 1/2 and reflected in the x and the y-axis. So what we have here, they tell us that our scale factor, they tell you the scale factor is 1/2, but they say we have to do a flip. So you're saying 1/2 is what's being changed. It's 1 divided by the a value, and our a value change is 1/2. So technically when we do 1 divided by 1/2 actually becomes 1 over 1 times 2 over 1. That's why we get a whole 2. So our a value is actually a value of 2. So then they did our graph. It says in the horizontal plane, horizontal compression, the x-coordinate of each point on f of x is multiplied by the scale factor to find the corresponding points. So we took our original equation, and this is our new graph that they want us to have. So it's being compressed with it. In example 4, they want us to do a vertical dilation. It says describe the dilation and reflection in g of x. It's equal to negative 2/5 x as it relates to the parent function. Because g of x is a linear function and the parent function is always going to be f of x equal to x, our parent function, they want us to say that f of x is equal to x and g of x is equal to negative 1 times the a value times f of x, where in this instance our a value is now going to be 2/5, because we're taking our original given piece, g of x, they tell us the a value is negative 2/5, and it's negative 1 times the a of the original. So when they did that, our f of x equation was a reflection and rotation. So here is our original. This is like your parent graph, y equal to x. This is the one representing y equals negative 2/5 with an x. Notice that we are downhill, which means this is a decreasing situation. The function is multiplied by negative 1 and the constant a after it has been evaluated. 0 absolute value less than the absolute value of a, less than the absolute 1. So the graph is compressed vertically and reflected in the x-axis. So the graph of the g of x equal to negative 2x is the graph of the parent function compressed vertically and reflected in the x-axis. Transformations of functions. So the general form of a transformation equation is always going to be g of x equaling a times f parentheses x minus h closed plus k, where f of x is the parent function. Each constant in the equation is going to affect the parent graph. If the value of a is absolute value, again, the value of absolute value stretches and compresses, which means it's going to dilate it. If the value is negative for a is negative, it's going to be reflected over the x-axis. If the h value is going to translate, it's going to be the one that's going to change it left and right. The k value is going to translate up and down. Our transformations of functions, when we're looking at this graph, these graphs here for the dilation, the blue is the parent. The maroon colored graph here that they show us is if your a value is between 0 and 1. And then the gold piece is if the a value is going to be greater than 1. When we look at our reflection, obviously if it's a reflection, the a value was negative. When we look at a horizontal translation, again, parent function is in blue. If we shift it to the right, means inside the parentheses we are a minus sign. If we shift to the left, the inside of the parentheses is a plus sign between our pieces. Our vertical translations, again, the blue is the parent. So if we had a plus k value at the end, we went up. If we had a minus k value at the end, then we went down. In example 5, they were going to have us do multiple transformations of functions. So it says graph g of x, the transformation of f of x equal to absolute value of x compressed vertically. So they want us to compress it vertically by a factor 2/3, reflected over the x-axis, translated 3 units left, and then up 1. So they set it up for us saying because f of x is equal to absolute value of x, they have our equation, g of x equals a times f of x minus h plus k. And we already knew what a is. They told us what a is. They said it's going to be a factor of 2/3. So in this instance, it's going to be negative 2/3 because it's being reflected on the x-axis. So we had to change the sign. The h value is going to be negative 3 because it's being shifted to the left 3 units. The k value means it's being up 1 piece. So when we had our original problem, we are saying f of x equals absolute value of x. So now I'm applying what they just told us to do. They're saying are being reflected. So that means I'm going to be negative 2/3. We are shifting to the left. In order to shift to the left, the number is going to be a positive value inside. And we're shifting up. So our new equation looks like this. So here's our problem. Here's our parent function. First thing I would do is reflect it. You're going to reflect it by a power of negative 2/3. So you're basically, if you do a table of values, you're saying negative 2/3 times x. Do your reflection first. Then, after you've reflected your graph, So if I had reflected my graph, I would have just done a table value saying -1, 0, 1, and I'm multiplying by -2/3. So we are at +2/3, 0, 2/3. So I would have plotted points where I was at 0, 0, -1 2/3, so I'm about there, and then 1 1/3, -1 1/3, flipped. And then I would have done my shift. So you'd have gone to here to your reflection and then shifted your graph to where it needed to be based on the locations. In example 6, it says suppose the dolphin during a jump is modeled by, and they gave us an equation. They gave you the equation for you they want you to use, where x is the horizontal change distance traveled, and g of x is the height above the surface. It says describe how g of x is related to its parent function and interpret the function in the context of the situation. So first thing, we need to write what we have based on the original equation. Okay, so we know that our a value in this instance is -0.125 from the equation. So we have our equation, and you identify the key parts that they give you. We have -1.5, x minus 12 squared plus 18. So when I look at my pieces, this is A, here is my H, here is your K. So our H is going to be +12, because remember, it's a negative on the inside, and you have to think of it as x minus 12 equals 0, so x equals 12. And the K value happened to be +18, so it stays +18. So when I'm looking at my problem, since 12 is bigger than 0, the graph is going to be translated 12 units to the right. 18 is bigger than 0, so the graph is going to be translated 18 units up. Now the dilations, though. Since 0 is less than the absolute value of -0.125, which is less than 1, since it's in between 0 and 1, we are going to be compressing our problem. So it's going to be compressed vertically. And because the a value happens to be negative to begin with, our graph is going to be a reflection in the x-axis. When we look to interpret the function, it says because a is negative, the path of the dolphin is modeled by a parabola that opens down. Remember, here's our graph, and the dolphin jumped up and came back down. So our dolphin, it's opening down because it jumped up out of the water, and then came back in. So it's opening down. This means that the vertex of the parabola HK represents the maximum height, the max height of the dolphin, 18 feet at 12 feet from the starting point in the jump.